All right, so let's start then our discussion. So last lecture, if we go back and look at what we had done was we had taken a look at this differential amplifier, and we had done a bias point analysis of this differential pair, and we said that the bias point analysis is pretty straightforward. All we need to do is when you remove the signal, the voltage here is minus 0.7, and given a VE, you calculate the emitter current here. So emitter current is, the current in the RE is calculated, and because the transistors are identical, Q1 and Q2, the same current flows in both of them, and that current is half of this IEE here. So, and once you know the collector current here and collector current here, what you do is you subtract out the drops here and the drops here, and you get the DC value or the bias point value of these two voltages here. All right, so today let's look at the small signal analysis. In small signal analysis, what we'll do then is, and remember, a small signal can be a DC or an AC, or it could be anything. The only requirement is that the signal be small enough for the amplifier to be treated as a linear amplifier. So linearity is all that you require, and for that you have to ensure that the signals are small enough. So what we do in this differential amplifier is that the first thing that we do is the two input voltages that are given to you, V in 1 and V in 2. Using these two input voltages, you define a differential input voltage, which we had seen earlier, V in 1 minus V in 2, and you define a common mode input voltage here, which is V in 1 plus V in 2 divided by 2 here. So there's a common mode input voltage and there's a differential mode input voltage here. So you can define these two quantities given the two input voltages that you see here. Now, what is interesting is that we can now, V in 1 that you see here, we can describe in terms of VID and VIC here. From these two equations, I can solve for V in 1 in terms of VID and VIC, and I can solve for V in 2 in terms of VID and VIC here. Alright, so this is what we have done here. V in 1 that you see here can be written in terms of a differential input voltage and a common mode input voltage here. And V in 2 can also be written in terms of a differential input voltage here with a minus sign and a common mode input voltage of VIC. So these two equations follow from these two over here. Now, what this allows us to do is the following. We can now take V in 1 out from here and replace it by two voltage sources in series. One is 0.5 VID, the other one is VIC. And we can take V in 2 out from here and replace it by minus 0.5 VID and VIC. So we can do that and we get the following differential pair. Note, I have removed the bias, the supply voltages now. This is ground here and this is ground here. And so this is my V in 1. And this is my V in 2. So these are the two voltages that we have replaced it by. Now, what we are going to do is the following. All right, so this is the now the differential amplifier in the small signal condition. We're going to replace it by two circuits here. Now, remember, under small signal condition, this is a linear amplifier. And when you have a linear amplifier, a linear system, you can use superposition. So eventually, what our interest is in finding what is V01, what is V02, small signal values of these two voltages here. Now, we can do that by using superposition. One, we know that V01 will come out, will result from these. There are four voltages in the circuit here. 0.5 VID here, minus 0.5 VID here, VIC here, and VIC here. Four different voltage sources that you see here. So we can write V01, we can determine V01 first due to 0.5 VID and minus 0.5 VID. First due to only the differential voltage here. Okay, note that in this circuit, there is no common mode voltage here. If the common mode between these two is 0, and there is only a differential signal here. So, and we can solve this particular circuit where there is only the common mode part here. So the idea is that if we determine V01 under this condition with VIC only there, and we determine V01 under this condition where we have VID only, then we can sum them up and get V01 under this condition. So we'll use superposition. So superposition will allow us to determine V01 here by solving for V01 here, where the signal is only differential mode, and for solving V01 here, where the signal is primarily common mode. Alright, so that's the strategy that we'll use here. And similarly, any voltage, any current that you want in your circuit, you can determine by first solving it where the input is completely differential in nature, and then by solving where the input is completely common mode in nature. And then you sum these up together to get the total value of V01. Okay. So then small signal analysis, as you can see here, can be broken into two parts here. One differential mode analysis and the other one common mode analysis. So the idea is that if any signal anywhere in your differential amplifier, we know that is made up of two parts. One is the bias part here, which is the quiescent point, and the other one is the small signal. That's a very general definition of any signal in any amplifier. It has a bias component and a small signal component here. All right. The small signal component in a differential amplifier can be further broken into two parts here. A differential part here and a common mode part here. Okay. And the differential part will depend only on the differential input voltage here related through some parameter here. If both of them are voltages, then this is gain. If one of them is a voltage, if one of them is a current and this one is a voltage, then KGD will be equal to conductance here. All right. So the differential part will be related to differential voltage here through some constant. Similarly, the common mode part will be related to common mode input voltage here through again some proportionality constant. Okay. So the idea is any voltage at, if you're interested in a voltage at this point, the voltage can be written in this manner. A bias point value plus a signal value, and the signal value can be broken into a differential part here and a common mode part. The differential part comes about because of the differential input voltage. The common mode part comes about because of the common mode voltage here. Now I've written X, meaning that it could be V01, it could be V02, it could be the current going into the base, it could be the collector current, any signal, whether it's voltage or current, has these two components. And similarly, the small signal component in general has these two components. Okay. So as an example, V01 that you see here, the total value of V01 will have a bias point, quiescent point, plus will have a differential part here and will have a common mode part. The differential part, V01, will come about because of differential input voltage here. So we can write this as the differential part, V01 equal to it depends on differential input voltage here, and the proportionality constant, we call it differential mode gain. So V01D here, referring to the differential part here, is related to differential input voltage, and this is the differential mode gain. The common mode part here, V01C, is related to common mode input voltage here through what we call as common mode gain. So that's how you find the net value of V01. A bias point value, a differential part value coming about because of differential input voltage, and a common mode value coming about because of common mode input signal. So how many analyses do we have to carry out? 3. A bias point analysis to give you this one, a small signal differential mode analysis to give you V01D, and a common mode analysis to give you V01C. So 3 analysis is what you have to do, because we have broken our small signal analysis into 2 parts, differential and common mode. Alright, so now what we'll do is, we have already done the bias point analysis. Let's do the differential mode analysis here, and then we'll do the common mode analysis. Alright, so in differential mode analysis, note, the signal is purely differential. On one side I have 0.5 VID here, on the other side I have minus 0.5 VID here. If you take the average of these two, the average is 0, which means there's no common mode signal in my circuit at all. That's why we're calling it pure differential mode analysis. And in this analysis, I would like to find out, when the signal is purely differential in nature, what is my V01, what is my V02, or what is the current that is going in small signal current. And if we know the small signal current, then we'll know what is the input resistance. Alright, so the way we do this analysis is we use symmetry. If you look at this particular circuit, Q1 and Q2 are identical, resistors are the same, and RE is common. On one side you apply a positive voltage here, on the other side you apply a negative voltage here. And what can we conclude from here? If we look at this particular node, what do you think it will be? This node right in the middle. On one side you have positive, on the other side you have negative, and the middle node will be 0 because of the symmetry. It can't be anything else. This particular voltage will try to make this voltage positive. Will try to raise this particular value to a positive value here. This one will try to raise, will cause it to go to a negative value here. And therefore, because of symmetry, the two will balance each other, and the net value will be 0. So that's one of the key points in the analysis, in the differential mode analysis. Because of the nature, because of the symmetry here, you apply positive here and you apply negative here. This point becomes ground. 0 volt here. Now, what kind of a 0 volt? Note that we are doing a small signal analysis. So it's not really your real ground. It's a small signal ground. Okay? It's a small signal ground. All that you're saying is that this is under small signal analysis, you can assume that this point is at 0 small signal voltage here. It's not a real ground here. Okay? Real ground is over here. That's the real ground here. This is more like a small signal ground here. So then, once this is 0, note that what happens is our circuit then separates out. The left half, if this is ground here, so this will become ground here, and this will become ground here. So the two circuits, they separate out. Earlier they were coupled together through REE, but the moment we realize that this is 0, the two parts separate out, and the left part is here, and the left part is here. And then we can clearly see that this is nothing but a common emitter amplifier. Common emitter amplifier with an input which is 0.5 VID, and so the output V01D is going to be nothing but minus GM times RC. Okay, so V01D, which means the differential part of the small signal voltage here, will be equal to the input here. Input is 0.5 VID, so 0.5 VID here, multiplied by minus GM RC. So that's the gain of this particular amplifier, which is a common emitter. So thereby, we have found out what is V01D here. Similarly, the other half, if you look at it, the other half, V02D, this is also a common emitter amplifier, but the input is minus 0.5 VID here. So V02 differential part here will be related to this one through a gain, which is again minus GMRC. So V0, but minus and minus cancel each other. So we get V02 differential part as 0.5 GMRC VID. So finally, then the relationship between differential, this voltage here, and this voltage and the differential input voltage is what we call as the gain here. So V01D divided by VID here is what we call as the differential mode gain, and that value is equal to minus 0.5 GMRC. Okay, which means that the output here, the differential part of the output here is related to VID through this particular gain, which is 0.5 times GMRC. So this is what we call as the differential mode gain. Note, you can take the output here, or you could also take the output here. If you take the output here, then the gain has a minus sign here. If you take the output here, then the gain doesn't have a minus sign. It's the same value. Magnitude is the same, 0.5 GMRC. The magnitude is positive. Okay, so you could take the output here, or you could take the output here as well. There's another possibility. You could take the output which is the difference between these two. Right? If you take the output which is the difference between these two, then this is minus 0.5 GMRC. This is 0.5 GMRC. If you take the difference, it will become simply GMRC. All right. So there are three ways of taking an output voltage. You could take the output here, or between these 2 points. Okay. So V01D we just saw 0.5 GMRC VID. V02 is plus here. So note that the output voltage here and output voltage here are exactly the same, except for 180-degree phase shift here. And as I said, you could define a differential output voltage here, which is the difference between the two, and that will be equal to GMRC. Okay. All right. So that's as far as the gain is concerned. We can also find out the input resistance here. Note that we are doing differential mode analysis. So when I apply 0.5 VID minus 0.5 VID, of course, from the input, some current is going to flow here, IID here. And because of the symmetry, if the current 0.5 VID sources a current like this here, then a same current will come out from here and will go into this particular source here. So my differential input voltage is defined, differential resistance is defined as the net differential voltage, which is net differential voltage is this minus this, which is VID, divided by the net current which goes into my amplifier, which is the IID here. So that's called the differential input resistance here. And it's very easy to see what this value is. Note that under differential mode analysis, this is small signal ground here. And we are talking about how much is this current here, this voltage divided by this current. And that is nothing but, what is the resistance between these two nodes? R pi. So IID that you see here, the current that goes in is equal to 0.5 VID, and the resistance that is there is R pi, and therefore my differential input resistance is nothing but VID by IID. That's the definition of differential input resistance. That's equal to 2 R pi. Okay. The 2 is coming because on one side we have 0.5 here, the other side is minus 0.5. That's why the 2 is coming here. Okay. All right. Output resistance. Well, the resistance looking from here, we know that if you look at resistance from here, resistance looking down is very large. Resistance looking up is only RC. So the output resistance is simply equal to RC, just like a common emitter amplifier. Okay. So we have determined the differential gain. We have determined differential input resistance. We have determined the output resistance here. And so that's the summary here. ADM is minus 0.5 GMRC, R0 is RC, RID is 2 R pi. And note that if I multiply them together, ADM multiplied by RID divided by R0, we get the same value, beta, just like a common emitter amplifier. Because we know that under differential mode analysis, your differential pair reduces to a common emitter amplifier. All the expressions that you see here, GMRC, RC, R pi, these are all for a common emitter amplifier. Okay, so basically, then the characteristics are just like a common emitter amplifier. Okay, and remember, we started out by attempting to build a common emitter amplifier where we didn't use a capacitors for biasing and for coupling of signals here. And so that's what we achieved. We achieved an amplifier which has similar characteristics as a common emitter amplifier, identical characteristics as a common emitter amplifier. All right, so that's the differential part here. Note that when I apply a signal, I have differential and common mode. So let's look at then the common mode part here. Because the input signals, remember, go back, keep this picture in mind. Keep this picture in mind here. The actual signal is here, V in 1 and V in 2. The actual signal then is broken into two parts, 0.5 VID minus 0.5 VID here, VIC here and VIC here. And we are breaking this pulsing analysis into differential part and a common mode part here. Okay, so keep that picture in mind, and then let's go to the common mode part here. All right. So common mode part, then we have only VIC from this side and VIC from this side also. So again, what we'll do is we'll use symmetry in order to simplify it. Transistors are identical, same resistance on both sides, same voltage also on both sides. Okay, and RE is what is common. So what we do is the following. We know that so we are talking about small signal. The same small signal collector current will flow here and same will flow here. Exactly the currents would be the same. These two currents that you see here and the same emitter current would also flow here because of symmetry. Whatever emitter current is here, same emitter current would flow here. And these two emitter currents would add up at twice the emitter current of one individual transistor will flow through RE. Okay. All right. So this is what we have. What we can do next is the following. Go back and look at this picture here. REE that you see here, I can split it into two resistors. 2 RE in parallel with 2 RE. Okay. And so this is what I do. Correct? Now, because of symmetry, you would expect IE to flow here and IE to flow here. Remember, the net current that was flowing was 2 IE. And half of the 2 IE, 1 IE will flow here and the other IE will flow here. Now, what can we say? What is the current flowing in this wire? 0. 0 current means what? Open circuit. If it is 0, which means I can open it, so I'll cut it here. If I cut it, now the two circuits become decoupled from each other. This half is the left half and this is the right half here. Both are identical. Okay? So the two circuits, they they decouple from each other, and therefore, and note that the voltage here, this is what we are interested in, the voltage at this node. will be the same as the voltage at this node. Okay. So this is the left half here. And so we focus on V01. And now what will be V01 by VIC here? This is again a common emitter amplifier with a resistor to RE, and we already know how to do this. V01 by VIC will be equal to GM divided by 1 plus GM multiplied by the net resistor here, which is 2 RE multiplied by RC. So that's the net gain from here to here. Alright, so this is what we call as the common mode gain. So that's straightforward. So once we realize that we use symmetry to split the circuit, so we did it both in differential mode as well as common mode. In differential mode, this point became small signal ground. In common mode gain, twice the resistor appears over here, and then we obtain the expression here. The resistance now, if we look at from here, we know that when you look at from the base side, the resistance is R pi, and whatever is here gets multiplied by beta. So the net resistance, which we call as the common mode resistance, is R pi plus 1 plus beta multiplied by the net resistance here, which is 2 RE. So that's the common mode input resistance. And output resistance, of course, we know when you look from here, output resistance will remain RC. Okay, so that completes our common mode analysis as well. We have ACM, we have RIC, and the output resistance is RC. Note something interesting. So V01 is what we determined here, and V02 is on the other side here. Both are identical. Because of the symmetry here, both are identical. So if you take your output voltage between these two nodes, instead of taking an output voltage between here and ground, if you take output voltage between these two, then the output voltage turns out to be zero. Turns out to be zero, which means that if you connect between these two, it doesn't depend on VIC at all. Okay. And of course, what would happen in practice is that the transistors will not be exactly the same, Q1 and Q2. The resistors will also not be the same. So V02 and V01 will differ from each other by a slight amount here. So you won't get, if you take V01 minus V02, you won't get a value equal to 0 in practical cases, but you'll get a small value. Alright, so we have a differential mode gain, which is 0.5 GMRC, and we have a common mode gain, which is minus GM 1 plus 2 GMRE multiplied by RC here. And we saw that the ratio of these two is important, which is called as the common mode rejection ratio. So we can take ADM by ACM here, and simplification gives us 0.5 plus GM times RE. GMRC, they cancel each other. 0.5 here, which goes here, and we get 0.5 plus GMRE. Now we require from a differential amplifier, we require CMRR to be high. Now how high? Well, a good value of CMRR may be 10 to the power 5 or 10 to the power 4. Those are the values that are considered as good values of CMRR. Now the issue is, can I get that much CMRR from a circuit like this? Can I get, I have the freedom to choose the resistor here, and note that once you choose the value of the resistor here, the current gets fixed. Because once the supply voltage is fixed, supply voltage will be fixed by an application, let's say plus 12, minus 12, or plus 5 or minus 5. So if supply voltage is fixed, the moment you make a choice of REE, note that this is minus 0.7 here under bias point analysis, and supply voltage is there, the current becomes fixed. And if the current becomes fixed, the GM also becomes fixed. So as a designer, the only freedom that you have for altering CMRR is choosing the value of RE. Now this particular expression, if you just superficially look at it, it may give you the impression that I can choose very large value of RE and get a very large CMRR. But that's not true, because GM depends on current, and current depends inversely on RE. So what we can do is we can quickly analyze this expression a little bit in more detail. GM is ICQ by VT, and IC of this transistor is nothing but IEE, the current flowing in this branch, divided by 2 VT here. And so we can write CMRR as 0.5 plus IEE, RE by 2 VT. We just substitute GM. And note that IE times RE, the drop here in this particular resistor, is nothing but this voltage is minus 0.7. and this end is VE here. So this is equal to minus 0.7 minus VE divided by 2 VT. So in fact, the CMRR is independent of RE. Is independent of REE and is decided primarily by the supply voltage. And if I plug in the value of supply voltage, let's say minus 12, so this is minus 12, this is plus 12, the CMRR that I get is only 200. And note that if the supply voltage becomes smaller, if I'm running my differential amplifier at plus 5, minus 5, CMRR would become even smaller. And if it's a portable application, plus 1.5, minus 1.5, it would get even smaller. So the challenge before us is, this is a very simple differential amplifier, but doesn't give us adequate amount of CMRR. The ratio of ADM and ACM is not high for most applications. And therefore, we have to look for a method whereby we can improve the CMRR of this particular amplifier. Now, if you look at this expression, there are two things that I can do in this differential amplifier. Instead of RC, I can have something else. You know, I take RC out and I put something else instead of RC. Or I can take RE out and put something else instead of that. Q1 and Q2 have to be there. These are the Q1 and Q2, two matched transistors are the heart of differential pair. I can't take them out. If I take them out, then I'm not left with anything. So the only option that I have, if I look at a method for improving CMRR, would be, let's say, take RC out and replace it with something else. Take RE out, replace it with something else. Now, if I look at this expression here, this expression telling you RC is not affecting. RC is nowhere entering into my expression for CMRR. Okay, so it's telling you, and RE is what is entering into my expression here. So what it is telling you is that maybe take RE out and replace it with something else. And we'll see that you know, all along what we have been doing is taking resistors out and replacing it by a transistor. And once we do that, we take this out and replace it by a transistor, we'll see that you'll be able to get good CMRR. Large CMRR, and the CMRR would then no longer depend on the supply voltage also. You can get high CMRR even though you have supply voltages which are plus 1.5 or minus 1.5. So we'll see that later on. That's how we'll try to improve CMRR, by taking RE out and replacing it by a current source, by a transistor. All right, so that's for later on. Okay, let's take a quick example. So we have a differential pair here. Plus 12 minus 12 volt is the supply voltage. 6Ks are the collector resistance. RE is 5.65. So as usual, the analysis will start with bias point analysis. So we determine IEE, which is this current here. Remembering the voltage at this node. When you remove the input voltage here, remove means this is ground and this is ground. The voltage at this node is minus 0.7. And so we get IE, which is 2 milliamperes here. And then once you know IEE, then it divides equally between these two. So we get ICQ1 and ICQ2, which are half of this, which is 1 milliampere. So you get the values here. And of course, if you have 1 milliampere here, then you know that the drop here is 6 volt here. And therefore, the bias point or the quiescent point, quiescent voltage of this point is 12 minus 6, which is 6 volt here. And similarly, 6 volt here. So that completes your bias point analysis. The next thing is to find out the small signal. So you determine GM. And that's all you need, because R0 is much larger than these resistors, so we'll neglect it. And then we have to determine ADM, RID, ACM, RIC, CMRR, right? So let's see how well you're paying attention. So maybe take out a page and determine these values. ADM, RID, ACM, RIC, CMRR. Beta is 100. Default value is 100. Okay, so let's look at the solution then. ADM is 0.5 GMRC. The important point is to remember, I'm sure if, most people remember GMRC. There's a 0.5 also. 0.5 GMRC here. ACM is GM divided by 1 plus 2 GMRE times RC here. And therefore, The value and RID is 2R pi. So ADM is 115.38. RID is 5.2K. ACM minus 0.53. RIC, which is 1.14 mega ohm. RIC is equal to R pi plus 1 plus beta times 2RE here. And CMRR is 270. So note that the common mode gain is pretty large, 100. And differential mode gain is pretty large, 100. And common mode gain is half here. So common mode signal is going to get attenuated, while differential mode signal will get amplified by almost a factor of 100. Okay. All right. So anyway, this more. This particular one is more for attendance. So let's let's continue. There's one more point that I want to cover before we break for the day, and that is, as I mentioned, that now analysis that you can do are of several kinds in a differential pair. One was a bias point analysis. So in a differential pair, what you do is a bias point analysis where the signals are not there, and only due to supply voltages you determine what the voltages in the circuits are. So that's a bias point analysis. The other one is a small signal analysis where the assumption is that the signals here and here are small enough so that the amplifier can be treated in a linear manner. And small signal, you can do it under two conditions. One is differential and the other one is common mode. Now there's another case where you have a signal here, but the signals are not small enough. The magnitude of the signals are reasonably large. Therefore, you cannot assume your transistor to be in a linear mode. Okay, so small signal analysis will then not work. In that case, how do we do the analysis? Now, for simplicity, I'm going to assume that my differential pair, the signals that I've applied are either DC or they're very low frequency signals here. So capacitances and all that do not matter. Okay. So the signals now, there are no limitations on the signal. V in 1 and V in 2 could be any value, could be large, small, could be anything. And therefore, how do we carry out the analysis under that condition? So there's a current here, which is IEE here. And one of the assumptions that I'm going to make is note that as you apply a voltage V in 1 here and V in 2 here, as you apply the voltage here, the value of this particular node here will change. The voltage at this particular node in general will change. And if the voltage at this particular node changes, then the current which flows here will also change in general. But I'm assuming that although I said that the voltages here can be of any magnitude, I'm assuming that these voltages here, although large from a small signal point of view, they are not that large in comparison to supply voltage. Supply voltage is like 12 volt, and the signal that I'm thinking of applying here may be 200 millivolt, 100 millivolt, 500 millivolt here. And therefore, the value of this voltage will change, but the current, to the first order approximation, the current will not change much. So I'm going to assume that the current is relatively constant, i.e. Okay. As I said, later on we are going to replace this by a current source where that assumption, of course, is always true. The current remains constant here. Okay. So with that in mind, what we can do now is that this current IEE will be equal to the emitter current here and the emitter current here, sum of the two emitter currents. And if the transistors are of reasonably large beta, we can of course assume IE equal to ICQ1 plus ICQ2. Okay. I should not write now, this should be modified. I should not write quiescent point anymore. I should write IC1 plus IC2 here. Okay. So what we are saying is IEE will be equal to IC1 in this transistor plus IC2 here. Now, if we look at IC1 for this transistor will be equal to, this is like the saturation current of this transistor here, saturation current multiplied by exponent VBE1 by VT. This is the base emitter voltage of this particular transistor here. So we are using the relationship between collector current and base emitter voltage that we know holds for a bipolar transistor in forward active mode. Of course, there is a term here, 1 plus VCE by VA also, early voltage, but we are assuming that that term is small. Okay, so we are neglecting that. So IC1 is given by this expression here. This is the saturation current. This is area of the transistor multiplied by the saturation current density. So if you multiply them together, you get the saturation current. IC2 similarly, on this side, I can write it as, because remember Q2 is identical to Q1, so its saturation current is the same. So current that flows here will be equal to saturation current multiplied by exponent VBE2 by VT. It's base emitter voltage divided by VT. Now note here, as I mentioned at many places, there are, in the same amplifier, there are times when we will assume that the voltage drop is 0.7. It makes sense to assume 0.7 here. There are times when we cannot assume it to be 0.7 here. Here deliberately, we know that the base emitter voltage and base emitter voltage are a little different here. So that's why we are using this particular model here. If you just assume 0.7 here and 0.7 here, then you can't determine anything. Okay. So VBE1 here and VBE2 here. So we have IC1 and IC2 given here. Now the other thing that I note here is that if I start from ground here and go along this direction, come here and come here and write a KVL. Starting from this ground, going to the base of Q1, coming to the emitter of Q1, which is same as emitter of Q2, then going to the base of Q2, and then coming down to ground here. If I write a KVL, the KVL gives me, there's a V into missing here. So V in 1 minus VBE1 minus VBE2, there should be a minus V in 2, will be equal to 0 here. So KVL will give us V in 1 minus VBE1 minus VEB2 minus V in 2 equal to 0 here, which rearranges in this form. VBE1 minus VBE2 is equal to V in 1 minus V in 2. That's how the equation rearranges itself. And then what we can do is V in 1 minus V in 2, the difference of the two, we call it as a differential input voltage, VID. And once we know VID here, V in 1 minus V in 2 is nothing but equal to VID here. Then note that if I take the ratio of these two currents, IC1 by IC2, the ratio of these two currents will be equal to exponent VBE1 minus VBE2 by VT. And VBE1 minus VBE2 is nothing but VID. And so all that we need to do is take this expression here along with these two. And we are able to then, and noting that IE equal to IC1 plus IC2, we can now obtain an expression for collector current flowing here and collector current flowing here. IC1 equal to IEE exponent VID by VT divided by 1 plus exponent VID by VT. IC2 is equal to IEE divided by 1 plus exponent VID by VT. So we can determine what is the collector current that appears here and what is the collector current that appears here. And the two are going to be different because of the voltages that have been applied. Note that if VN1 equal to VN2, then my VID is 0, VID is 0 here, and the two currents then are the same. The two currents IC1 and IC2 are the same. All right, so once you know IC1 and once you know IC2, then of course you know the voltage at this particular node here and the voltage at this particular node here. So under this, now note that I have not put any restriction on V in 1 and V in 2. They can be, I can apply a 1 volt here. I can apply 0.5 volt here. It need not be small signal. It need not be small signal. So under this general condition, I have an expression for IC1 and IC2, and therefore I have an expression for V01 and V02. All right. So that's a general large signal analysis of a differential pair. Now there are several interesting things here based on these two. Okay, so I'm going to take these two expressions and I'm going to plot it out. I'm going to plot it out as a function of VID here. VID is V in 1 minus V in 2. So note that when VID, and this is IC1 and this is IC2. And note that sum of IC1 and IC2 is what? Is almost fixed, which is IE. So what is happening is when VID is 0, then the two currents are the same. IC1 and IC2 are the same. When you make VID positive, which means V in 1 is larger than V in 2, what happens is more of this current shifts to Q1 and lesser flows to Q2. So what happens is IC2 decreases and IC1 increases. And as you keep on increasing VID, the difference between the two, IC2 keeps on reducing and IC1 keeps on increasing. Eventually what will happen is, if you apply large enough voltage, then the entire current IE flows through Q1 and nothing flows through Q2. You can see here. Current through Q2 goes to 0 and the entire current starts flowing into my transistor Q1. So what has happened is, this current, you have switched this current entirely to Q1 and nothing flows through Q2. And how much voltage do I need to cause this switching? You can see here, close to about 100 millivolts. 100 millivolts is all that I require, 100 or a little larger than that, and the entire current that you see here, IE, is flowing through Q1, nothing is flowing through Q2. Q2 is almost like cutoff state. On the other hand, if I make V in 1 less than V in 2, which means VID is negative, now what happens is, IC2 starts increasing and IC1 starts decreasing. So which means what? This current now starts flowing more and more through Q2 and not through Q1. And if you apply a large enough negative voltage here, the entire current here, IE, shifts to Q2 and nothing flows through Q1. So this differential pair has then a very interesting property of current switching. You can switch, this current is almost constant. You can make this current flow equally between these two. You can make this current flow more through Q1, less through Q2. In fact, you can make IE flow entirely through Q1, or you can make IE flow entirely through Q2, depending on how you apply these two voltages. Alright, so very interesting property that you have a current source here, IE, and you can switch the current to either side here. You can switch this current here, or you can switch this current here. Okay, and note that, so by switching the current here, obviously the voltages here will also change. If you cause all the current IE to flow here, then the voltage at this particular node will drop and the voltage at this particular node will rise. Similarly, if you cause IE to flow entirely through this particular node here, the voltage at this particular node now will rise. In fact, it will become equal to VCC here. Okay, so this current switching that you can do, how do you switch the current? By changing the voltage here. And as you change the voltage here, the current switches between these two transistors, causing the voltages here to go up and down. And in fact, if you read books, you'll find that this differential pair was the basis of a very popular logic circuit called emitter coupled logic. And at one time, this was one of the fastest logic circuits available. If you want to build a very fast NOR gate or a NAND gate or whatever it is, this particular logic was used to build it. A differential pair was the heart of emitter coupled logic here. Okay, so that's a very interesting property which is frequently used here, that you can switch the current between Q1 and Q2. Okay. All right. So it's the same thing that I talked about is illustrating here. Note in this case, so in this case, V in 1 and V in 2 is there. So I've applied a voltage equal to VT, thermal voltage here, 26 millivolt. And note what is happening when you apply 26 millivolt. This is 2 milliamperes here. The current here has become 1.4 and the current here has become 0.57. A fairly small voltage causes substantial shifting here. One thermal voltage, 26 millivolt. Then I apply 2 VT. 2 VT causes 1.7 here, 0.27 here. And the voltages are changing. 3 VT, 1.87 and 0.11. And 200 millivolt, 2 milliamperes here, nothing here. So anyway, all you require is maybe 4 or 5 VTs that you can see here to cause the current entirely to shift to this side. Okay. Similarly, you can go on the negative side here. Minus 3 VT, the current here is 1.86, current here is 0.11. And you go minus 200 millivolt here, the entire current will flow here on this side. Okay. All right. So let's stop here, then we'll continue.